So in this section, we'll be talking about the magnetic properties of atoms and how it's related to their electronic configuration. So as you can see on the screen, there are three types of magnetic properties. We have diamagnetism, paramagnetism, and ferromagnetism. Diamagnetism is basically the weak repulsion that an atom or atoms will have for a magnetic field, and that is associated with paired electrons. Paramagnetism, on the other hand, is basically the opposite. It is the attraction associated with atoms to a magnetic field where there's unpaired electrons, right? So it's associated with unpaired electrons. So basically, when you think of paired electrons, diamagnetism would be the type of property displayed. In the case of structures which contain unpaired electrons, paramagnetism would be the type of property that would be displayed. And let me just say that in the case of paramagnetism, all you need is just one unpaired electron, all right, in order for paramagnetism to be the property displayed by such atoms. Then there's a third type of magnetism, which is known as ferromagnetism, and this is an exceptionally strong attraction that a magnetic field will have for iron and a few other substances. So let me just say that in this section here, we'll be concerned primarily with paramagnetism. So basically what we'll be looking for the most part, is that if you have a structure that has unpaired electrons, then this will display paramagnetism. Okay, so how do we determine this? Well, here is a schematic representation of how we determine the magnetic property of a substance. Basically, you have a tube containing the substance, which is attached to a balance, and right near to where the tube is, where the substance is in, we have two poles of a magnet. Over here, the magnet is not turned on yet, so there's no magnetic field. So what you can do is record the mass of this substance on the scale here, and then when we turn on the magnetic field, in this particular case, the magnetic field will have an attraction for the substance in the tube. So therefore, it's going to pull it towards the field, and therefore, the mass reading would increase here. So basically, by virtue of the fact that the mass reading has increased, then that means that this substance must have unpaired electrons and therefore must be paramagnetic, all right? So that's basically how we determine whether or not a substance is paramagnetic. And that is due to the fact that in the electronic configuration of the substance, it has unpaired electrons in it. Okay, so that brings us to this question. It says a sample of chlorine gas is found to be diamagnetic. In other words, it does not have any unpaired electrons. So the question is asking, can this gaseous sample be composed of individual chlorine atoms? So to answer that question, we have to first determine the electron configuration of chlorine. So if we do that, first we need the atomic number for chlorine, which is 17, and therefore we can determine the electron configuration, which is 1s2, 2s2, 2p6, 3s2, and then 3p5, and that gives you the total electron count. And on further examination, if you look at the way the electrons are distributed in the 3p sublevel, remember now there are 3p orbitals, right? So that means that the way the electrons are distributed is like this: 1, 2, 3, 4, 5, right? So basically, you have one unpaired electron here. So what that tells us is that chlorine atoms are paramagnetic, which means that gaseous chlorine is not made up of chlorine atoms. So the answer to this question is simply no, right? Because chlorine atoms are paramagnetic, but the chlorine sample that they're talking about here is diamagnetic. So therefore, the chlorine in that sample would not consist of chlorine atoms, and in fact, consist of chlorine molecules, which are diatomic, and therefore, what you'll find is that the electrons are paired up in that structure. And therefore, chlorine, the molecule itself, would be diamagnetic. Okay, we're going to stop here. The next video will deal with examination of the relationship between the electronic structure or configuration of an atom and its relative positions in the periodic table. And also we will look at certain periodic trends and properties of elements as you go across a period and down a group. All right? Okay, until next time.